Hello everyone, welcome and a very happy new year to all of you guys. So yes, on this day I am launching a video and we are going to be doing 7 important palladium catalyzed reactions. Yes, so we will be doing 7 important palladium catalyzed reaction in just one video along with the previous year question, along with the relevant previous year question. So yes guys, if you study on the first day of your new year, it is going to be a very good year for all of you. Alright, so let's talk about this. So the first reaction is Wacker Oxidation, Heck reaction, Suzuki Coupling, Sonogashira Coupling, Stille Coupling, Negishi Coupling and Kumada Coupling. So all of these, most of these are coupling reactions, okay? And other than that, we have Wacker Oxidation and Heck reaction. Okay, so there are more palladium catalyzed reactions, but in this video, we are going to study these 7. Okay, chalo, let's begin very quickly. Alright guys, before moving onwards, let me quickly remind you that I'm also an educator on the Unacademy platform and I teach in the CSIR UGC NET category for chemical sciences. If you want, you can join me on Unacademy for a lot of free classes, as well as I teach on Unacademy Plus. So what is Plus? It is a paid platform in which we are doing full syllabus study along with revision and practice and so on, right? So yes, if you want to join the Plus, you can use the code Jagriti S. And now let's begin. So the first one is Wacker oxidation. Let's quickly talk about this. Wacker oxidation is a very popular reaction and very popularly used in the conversion in the palladium catalyzed oxidation of olefins to mostly ketones mostly and aldehydes in certain cases. So only certain cases, but since our CSIR questions are mostly focused on the major product, we are going to be talking about ketones. Okay, so here guys, there's a whole bunch of catalyst and co-catalyst and stuff like that. Let's talk about this. The reaction mechanism is there in the next slide. So here the co-catalyst copper chloride CuCl2, in which the copper is in the +2 oxidation state like this, okay? So it reoxidizes the palladium 0 to palladium 2 plus in the catalytic cycle. There has been a question in your previous years ki what is the role of copper. So copper 2 plus reoxidizes palladium 0 to palladium 2 plus, and when the CuCl2 converts to CuCl, it is once again oxidized to CuCl2 by oxygen itself. Okay, so yes, this is a whole catalytic cycle which is happening. What does the mechanism involve, guys? What is happening with this whole mechanism? So the first step in the mechanism involves the coordination of alkene with palladium 2. So first of all, we are starting with palladium 2 plus, then it is going to reduce to palladium 0. Copper 2 plus oxidizes it to palladium 2 plus once again. Alright, so this is it what we have studied till now. Next step involves water attacking at the more substituted carbon to give hydroxy palladation. Okay, this is a very important step. ये जो hydroxy palladation step है, this is going to decide whether you have the ketone or the aldehyde. We'll see that. The next step involves hydrogen shift and reductive elimination. Reductive elimination to give you the ketone. Okay, so the final product is a ketone. Chalo. So what is the overall reaction? If you want to just write it down, overall reaction is like this. We are starting with palladium 0. It gets converted to palladium +2 while it is reacting with CuCl2 like this, and then CuCl forms. Copper becomes +1. Now the copper +1 is once again oxidized by oxygen and HCl to +2 once again. Okay, so this is a whole catalytic cycle, and meanwhile your alkene or your olefin got converted into ketone. So let's look at the whole process. I have just taken it down over here. So this is your olefin, for example. Okay, a simple substituted, right? So just mono substituted olefin we have taken over here so that we understand what is a ketone and aldehyde possibility. Catalytic amount of palladium chloride, and you have water, CuCl2 and oxygen as well. So it's not just metal catalyst, you also have oxygen in the medium, right? So this is your ketone that you get. Now let's understand the whole process. So it looks like very intimidating, but it's not. So ये देखो, we are starting with palladium 2 plus. Okay, very good. We are starting with palladium 2 plus. Now, most of these reactions, see, most of the palladium catalyzed coupling reaction, they follow a same mechanism. But most of these reactions, which are oxidation or Heck reaction, right, they have only a little difference in the mechanism, right? So first, let's consider the Wacker process. So your alkene is going to coordinate. अभी जो palladium 0 था, it got converted to palladium 2 plus because there is CuCl2 like that. Okay. So here it's palladium 2 plus. Now it is going to complex the alkene in this way. देखो, there is a complex formed between the alkene and metal like this. Yes. Now the water is going to attack, and this is the most important reaction of the whole cycle. Why? Because when the water is attacking, water has two possibilities. Water could attack on the terminal side also, like this. Water could attack over here also, but water gives the Markovnikov addition. Okay, but the water gives the Markovnikov addition, and it is going to attack on the more substituted carbon, and palladium will always want to go on the less hindered side. So after the reaction you will get something like this. Okay, there is palladium on the less hindered side, and there is this water. I've just directly removed the hydrogen. Okay, so yes, this is what you get. ये देखो. So you have your oxygen on the more hindered side, hydrogen on the less hindered side, right? Now you might call it a hydride shift which is taking place from here, or you also might call it beta hydride elimination. Okay, so from this carbon and from this carbon you are getting the removal of a hydrogen and palladium. So you might also call it beta hydride elimination. Okay, or you might also, in some books it is referred as hydride shift. That's all okay. Ultimately you're getting the ketone over here, right? After the hydride shift and the palladium removal, you are getting the ketone. First you will get the enol like this, no? Yes, first you will get the enol like this, but you know enol is going to tautomerize to ketone like this. So major product you have already got ketone. Why are we getting ketone? Because of this key step, Markovnikov addition of water. Okay, chalo. So we move onward. What happens with palladium now? Palladium, guys, is undergoing reductive elimination. Whose reductive elimination? HCl. So still palladium is there in +2 oxidation state over here. When it does the elimination of HCl, then it goes to palladium 0. Now once again, when the palladium goes to 0, we know that it is going to be reoxidized by CuCl2 to get back your catalyst into the place, and this whole cycle is going to go on. So what happens with CuCl2? CuCl2 does the reaction and gets inserted into this line of reaction, reacts with palladium, oxidizes it, and itself it gets converted into CuCl. ये हो गया इसका खुद का reduction. Now when we are adding oxygen, so oxygen, 0.5 mole of oxygen in HCl, when it is reacting with CuCl, then it gets reduced to H2O and oxidizes copper to copper 2 plus. So these are interconnected chains, and this is how it is written. Very simple to interpret, nothing very huge. This is your Wacker oxidation. Let's move onwards and see this example. So isn't that very obvious that over here you just have only one olefin? You just have only one olefin bond, and whenever you see palladium with copper and oxygen, when you spot this reagent, you must know that this is Wacker oxidation if you also see the olefin, and you must know that it is going to give you the ketone, not the aldehyde. Yes, and the remaining stereochemistry of the molecule remains as it is. It is not even touched. This part is not even touched. Okay, you're just getting the ketone. Alright guys, chalo, let's move onwards very quickly. All of these are other reaction conditions which we don't need to worry about over here. Let's look at our second reaction, that is your Heck reaction. Now there is a difference between all the other reactions and Heck reaction, because this once again is not a coupling reaction, although there is a new carbon-carbon bond formation which is taking place, but it is still not a coupling reaction. Let's see. So it is palladium catalyzed alkylation or arylation of olefins, okay, which means that you are adding something to your double bond. Wacker oxidation was oxidation of double bond. Here it is addition to the double bond. ये देखो. Okay, so let's just see this example first. You have your iodobenzene. You have this double bond over here, which is your alpha beta unsaturated ester. Now, if you look closely, your carbon from here and your this carbon, they are terminal carbon, they just got connected like this. They just got connected, iodine got removed, and one of the hydrogens also from here got removed, because otherwise it is not possible. So iodine got removed and one of the hydrogens got removed, and they just got connected. Looks like a little bit of a coupling reaction, but the mechanism is different from the coupling reactions. Let's see. So first of all, oxidative addition of palladium 0 into a unsaturated halide takes place, or triflate, okay, followed by reaction with alkene. Okay, so what just happened? Oxidative addition of palladium into unsaturated halide or triplet. What are triplet? You usually write triplet as OTF because these are very good leaving groups. So halide or triplet, they are going to give the same reaction, right? So first of all, oxidative addition यहाँ पे, right? Then addition with alkene, leading to overall substitution of vinylic or allylic hydrogen atom with unsaturated group. So exactly what we are doing, we are replacing one hydrogen atom with unsaturated group like this, and specifically this is for your unsaturated halide, your vinyl halide or phenyl halide, something like that, right? So here you have palladium acetate, palladium in the 2 plus oxidation state, triethylamine, which is your base. Chalo. So first of all guys, what happens is, see, there is one thing, you have to take palladium into 0 oxidation state first of all, because this is a little bit of a different reaction, right? So what happens is your amine ligands, either your amine is given or phosphine is given sometimes, right? So it will convert the palladium acetate to palladium phosphine complex like this. So most of the times this is what you see. This is what you see. So you see palladium in the 0 oxidation state. Okay, right. So here we are, iodobenzene and your palladium acetate over here, which is going to be converted into 0 oxidation state, right? So after going to 0 oxidation state, when palladium is 0, the first step is oxidative addition of palladium. Now oxidative addition requires the palladium to be in the 0 oxidation state, because if it is already +2, it cannot go to +4, right? That will not be possible. So it has to be 0 oxidation state, then it goes to +2. Okay, simple reaction. So here you have palladium inserted or oxidative addition. Now, just like the hydroxy palladation step in the Wacker process, here we don't have hydroxy palladation, here we have addition. So palladium adds to one of these carbons and your benzene adds to one of these carbons. Okay, so here there is no rule as Markovnikov rule. So your bulky group is always going to be on the terminal. So this is your bulky group and it goes on the terminal like this. Okay, so there is how it is. Now this process of addition to alkene is specifically called syn addition. And why is that so, syn addition? Because both of these groups, both of the palladium and the phenyl ring, they are added from the same side. Okay, so if they are added from the same side, we would rather write it both of them above the plane, as I have written. Yes, so as I've written, both of the palladium and the phenyl ring are above the plane. Okay, very good. So this is a minute detail you have to know. After the syn addition has taken, there is going to be beta hydride elimination. I have already told you this. Beta hydride elimination also has to be syn. Matlab it also you must have the palladium and the hydrogen on the same side. So how are you going to do that? You just added palladium and benzene on the same side. So you can rotate, isn't it? Yes, this side is free to rotate. You will rotate and you will get this lower hydrogen coming up towards palladium, something like that. If you do that, your conformation is just going to change only a little bit. We are not completely changing 180 degree or 120, we are just rotating 60 degrees, just rotating 60 degree this carbon, right? So देखो, this hydrogen is going to go on the top, this hydrogen is going to be like this, और ये phenyl ring जो है, it will now be on the plane. Okay, so this is how we rotate. And yes, ये देखो, if you want to number it is HA HB, ठीक है, that will make it clear. So we are rotating like this, right? Your phenyl, once it was above the plane, now it becomes on the plane of paper. Your HA is on the top, your HB is still below. Okay, yes, so just you are rotating. Alright, so here we are guys. After rotation, you see that your hydrogen and your palladium are now on the same side. So if they are on the same side, you can carry out beta hydride elimination, and that is going to give you an E alkene. So Heck reaction, most of the time it gives you E alkene. Most of the time it gives you E alkene. So I just told you why do you get E alkene. If you don't want to remember the whole mechanism, you can just remember that Heck reaction is going to give you E alkene most of the times. Okay, yes, so here we are guys, done with Heck reaction, Wacker oxidation. Third reaction is Suzuki coupling. I know that you already have heard about this a lot of times. So it is a palladium catalyzed cross coupling. Now these cross coupling mechanisms are way too easier. Okay, so it is cross coupling of organoboranes with organic halides, triflates, etc. So whichever is a good leaving group, we just need a good leaving group. So what happens in the cross coupling reaction is your oxidative addition, transmetallation, reductive elimination. 3 steps. Okay, very simple. So here you are with your alkyl halide or alkenyl or aryl halide. Okay. Then you have organoborane. Like you have BCH3 whole thrice, you can replace this methyl with some other group also. Yes, so this is your organoborane, and we are going to do coupling in the presence of palladium. You require a little bit of base, for example K2CO3, something like that. Base is required. Why that is so, that I'll tell you. So base is required and you get the R dash coupling in this way, right? So let's do the mechanism first of all, and let me tell you why is base required. So this is your alkyl halide. Alkyl halide will undergo oxidative addition. See, the palladium has to be in zero oxidation state, which in all these reactions where first step is oxidative addition, because then only it will go to palladium plus 2. Yes, very simple. Oxidative addition. Now oxidative addition takes place in such a manner that your R and X are added in this way, right? Then comes your organoborane. Organoborane say we want to grab this R1 and we want to do transmetallation. So what is transmetallation? Just swapping, just interchanging, that is transmetallation. So this X is going to come to boron and the R dash is going to come to palladium. Yes, that is how it happens, transmetallation. But there is one problem, it's not that easy. Why? Because boron guys, okay, transmetallation sounds very easy, but it's not that easy for boron, because boron is a Lewis acid. Why will it try and give the R1? Why will it give it's one of the alkyl group? It will not do that until and unless there is a base. So the base is going to make the borate ion, right? Like this, R dash. Okay, and there is R2, another R2 and OH. Now the boron has a negative charge. Now the boron will be able to eliminate one of its alkyl group very easily. So here you are, you have a base NaOR3. For example, it could be OH minus OR alkoxy base and so on. So you got your base, and the R1 will now be very easily able to do transmetallation, as you can see with palladium. So R1 goes to palladium and X is going to go with boron. Yes, so here we are now, R and R dash both on palladium. Palladium can now do reductive elimination directly to give you palladium 0 and your ligands. So this is your RR dash. Okay, so we have to take care that Suzuki reaction is the coupling reaction of your organic halides or triplates with organoborane. Suzuki reaction, borane. Okay, so this is what you have to remember. Second thing, there has to be a base. So boron and base are easy to remember, no? B say boron, B say base, like that. Okay. Chalo. Now we see another simple coupling reaction. So when we talk about coupling, it is oxidative addition, transmetallation, and reductive elimination. It's that easy. Just that in different name reactions, we are changing the metal with which the transmetallation is taking place. So in Suzuki, we had the boron, or let's say the borane, in which we are doing transmetallation. In Sonogashira reaction, we are doing, yes, palladium cross catalyzed cross coupling of organic halides with terminal alkynes, as you have might have seen in the exam a lot of times. Ye raha. So it is your terminal alkyne. Here you are using copper and triethylamine, okay, in the Sonogashira coupling. So alkyne, copper and palladium. Yes, this is it. So what is the overall reaction? You had this alkyl group, you had the terminal alkyne. Both of them are coupling and giving you yes, this alkyne system over here, substituted alkyne over here basically. Okay, that's the coupling reaction. Let's see the mechanism once again. For example, you have palladium PdCl2 triphenyl phosphine, bis triphenyl phosphine, like this. Okay, palladium is there in the +2 oxidation state. We are taking it to 0 oxidation state by various important steps. Okay, chalo. So now if the palladium is 0 oxidation state, it will undergo oxidative addition. But whose oxidative addition? Your RX bond. It could be alkyl or alkenyl halide. It is usually, it is a vinyl halide, or it is your aryl halide, right? Something like that. It is most frequently used because doing reactions on these unsaturated carbons is more difficult as compared to your simple sp3 carbon, right? Okay, so oxidative addition of palladium into Rx is going to give you R and X in this way added on to palladium. Now, here what just happened on the side, you directly see that there is a R dash Cu triple bond C, matlab ki you directly see that somehow there was this alkyne and somehow copper has got attached to it. Yes, how does that happen? You had copper 2 plus. Okay, now let me just check. No, you had copper 1 plus. Copper iodide tha. So copper 1 plus, right? How did that happen? So for that you have the triethylamine. It is not a very strong base, but your alkyne proton is also acidic, right? So it can donate the proton very easily, and it can form the alkynide anion, which is going to be stable with the copper cation, like this. Okay, so your copper cation is going to, now this is going to basically do the transmetallation. Here is your transmetallation step. And in the Sonogashira reaction, just have copper doing the same thing, transmetallation. So your alkyne part goes to palladium and your X eliminates with copper. So here it is, palladium got connected to the alkyne part and your copper X got eliminated. Okay, now you have a direct reaction. You can do reductive elimination over here, yes or no? If you do the reductive elimination, you will get palladium back in 0 and your terminal alkyl got connected to a more substituted alkyne system. That is it, another coupling reaction. So copper Sonogashira reaction, copper and alkyne Sonogashira. Okay, chalo, moving onwards to Stille coupling reaction, guys. It's a very beautiful reaction, and once again the same coupling reactions are going to not give you a headache because they're all very similar. Palladium catalyzed cross coupling reaction of organostannins with organic halides, triplates, etc. Organostannins, that is your tin. You know, it's very easy to remember. S मतलब कि Stille coupling, S मतलब कि your SN, which is the tin. Okay, so this is how you can remember, right? Stille coupling means that you are using tin. Okay, once again the same reaction. You have Rx, oxidative addition by palladium 0. Then there is going to be tin with this alkyl group or any other alkyl group which is highly polarized, easy to migrate, right? So that is going to do transmetallation followed by reductive elimination, and this is your product. I hope that now without even telling me you can do the mechanism, right? So there is Rx, palladium doing the oxidative addition in between this bond over here. There is what you get. Now this is your transmetallation step. This was oxidative addition, transmetallation. ठीक है, where your R1 got connected to palladium in the replacement of X. It could be R1 also, it could be R3 also, just that a more polarizable group is going to transfer, or let's say the one which has very weak bonds with tin, that is going to transfer. So now finally you do reductive elimination step. Your R dash and R are going to get eliminate like this, and your tin takes away the X group. Okay, and palladium, once again you see palladium in the zero oxidation state. So this is a whole cycle. I've just opened up the cycle and writing in a linear line, but ultimately you are starting with palladium 0, you're getting back to palladium 0, doing all of this reaction. Okay, chalo. So for example, I just asked you a very simple question over here. What is the major product of the following reaction? For example, so guys, here what do you see? You have palladium, you have copper, you have tin also. Okay, so with copper, you usually get the Sonogashira reaction, but that is copper and alkyne. You don't have the alkyne, so copper has a different role to play over here, right? It is not Sonogashira reaction. So first of all, there will be oxidative addition, transmetallation, reductive elimination. You have to find out that there is one position over here, one position over here. The other two are same, as you can see, because there is a sigma plane bisecting the molecule. So these two positions are same, these two are same. So we would just say that there are two possibilities of product formation. Which group is going to undergo oxidative addition? That is very, very obvious, guys. That is, your bromine is more polarizable as compared to chlorine, and hence, sorry, there's a bromine over here as well, and hence this is what you get. You are not getting oxidative addition on chlorine because bromine is present. Also, bromine is present at a very, very at a position which is taking away electron density, right? So minus I effect of nitrogen is working over here, and this is supposed to polarize the bromine bond very, very nicely. So hence you are getting the oxidative addition on this carbon. So your transmetallation would take place like this. Let me just write it. So the transmetallation would take place in this way, that there is a nitrogen, there is another nitrogen. Okay, there is a simple Br. After the transmetallation, there is a palladium, and from this carbon, from the second carbon, take care of this second carbon. From the second carbon, you are doing the transmetallation, SO2PH. Okay, and then there will be reductive elimination to form a bond in between these two. So be very careful about the position. Now, so the position is right over here, and this is connected to the carbon having Cl. So it is wrong. A is wrong. Once again, it is your second carbon, okay, and connected to the side having bromine. Looks like correct. Okay, what about the other one? Ye dekho, there's a problem in the position. It is your third carbon. It is also your third carbon. Not happening. This is completely not happening. Okay, so there is no isomeric shift or anything like that in palladium catalyzed coupling reaction. Exactly the same carbon and same stereochemistry is also conserved. So your answer is option number C. Let's do one more name reaction, that is your Negishi coupling. So once again, coupling reactions are so easy. So it is a nickel or palladium catalyzed cross coupling of organozinc compounds with various halides or triplet. So once again, you are focusing on zinc, RZN. So you are working on RZN compounds, your organozinc compounds in the Negishi coupling. Isn't that very easy? So yes, you have your alkyl halide, you have your alkyl zinc halide. First oxidative addition takes place right over here to give you RPDX plus R2, or let's say R dash diya hua hai, so R dash zinc. Why? You will do transmetallation, then you will have palladium R dash over here, ZnXY, like that. Let's say it is ClF, ClBr and so on. ठीक है, ये वाला, this is going to get eliminated. So reductive elimination, you get R dash and palladium in the zero oxidation state. It is not that it is a single element which is palladium going to eliminate. No, it's not the metal. It is with your neutral ligands, for example phosphine, amine and so on, neutral ligands, right? So hence no charge. Okay, so if you want to check out the mechanism, once again here it is. I know, but you have already learnt it by now, the cross coupling reactions. So palladium in zero oxidation state, oxidative addition, you get +2 now. Now this step is going to be transmetallation, like here. So transmetallation, how does it happen? Palladium is attracting the R dash group or the alkyl group, and zinc is attracting the another halide molecule, halide atom, right? So this could, you could write it like this. It is not always the case though, but ऐसे लिख सकते हैं. Then you have ZnX2 and palladium having your L number of ligands, neutral ones, R and R dash. You do reductive elimination, it will be R and R dash, like this. So this is your alkyl carbon-carbon new bond formation once again in the cross coupling reaction. Similarly, we'll do one example of Negishi coupling over here, as you can see. So the molecule, it has OTBS and it has I. So you might get confused that who is going to leave over here. But guys, your iodine is going to leave because it is going to undergo this your palladium catalyzed reaction. It is going to undergo oxidative addition first. Or let's say what is it written in the first step? You have tertiary butyl lithium. Okay, now the tertiary butyl group, it is going to actually grab the iodine and get a negative charge onto this carbon, which is going to stabilize zinc 2+. So ultimately you are getting ZnCl, and there's a methyl over here, and there's another methyl over here, and OTBS over here, like this. Okay. Okay, so this is what you have, guys. Now after that, when palladium is there with another molecule, it is going to undergo oxidative addition into this single bond right over here, and there is going to be a coupling. So coupling between this this carbon and the other carbon, that is your alkene carbon over here. So this is the new carbon-carbon bond which has formed over here. Okay, so once again it is your Negishi coupling having zinc. So guys, what you can do is you can make a chart of all of these palladium catalyzed reactions and try to remember. Chalo, we come on to our last reaction and then we'll solve PYQs. Your Kumada coupling. So Kumada coupling is another easy coupling, just that you have a change in the metal. Who is the metal? Metal is magnesium. Yes, exactly. You are using your Grignard reagent. So Kumada coupling mein, we are not using zinc or anything. We are starting with alkyl halide. We are using Grignard reagent in the presence of palladium. Not directly magnesium is going to react with this, but in the case of palladium, that is going to be another coupling reaction. So the process remains the same. First step is oxidative addition. Alright, so you get the R group and X on the palladium surface now. Then the second step is going to be transmetallation. The second step is going to be transmetallation, like this. Okay, so transmetallation will remove the X with the magnesium, it becomes MgX2 and it leaves. and your R dash and R on the same palladium. Reductive elimination gives you RR dash and palladium once again in the zero oxidation state. So all of the mechanisms are all exactly the same, but for the coupling reaction, not for Heck reaction, not for your Wacker oxidation. Okay, chalo guys. So another example if you want to see. Okay, so look at this molecule guys. Is it a molecule which is very easy to prepare from the electrophilic aromatic, or let's say any aromatic reaction, any organic reaction? Is it able to is it easy to form a bond between already two aromatic rings? Yes, not at all, because if you want to do the electrophilic aromatic substitution, which ring is going to give the substitution? Both of them are aromatic, right? So yes, that is why if we want to create rings like this, we will carry out palladium catalyzed reactions. Okay, okay, so here we are guys. So there is your bromine on furan, second position of furan. It will undergo oxidative addition like this. In this manner, it will undergo oxidative addition, palladium Br. Then there is going to be transmetallation between magnesium. So that actually gives you palladium and something like this. Yes, and the reductive elimination, or basically I should write over here, reductive elimination is going to directly give you this product. Okay, and along with that, palladium once again go to palladium 0. DPPF is your another phosphine ligand, another bisphosphine ligand, which is a neutral one. So hence palladium again goes to 0 oxidation state. So it's the whole cycle repeating in all of the coupling reactions. And yes, I hope that you will be able to remember all of these names guys. Chalo, let's do some PYQs. Now all of these are your CSIR NET PYQs. CSIR NET PYQs. Okay, so first of all, you have in the following reaction sequence structure of A and B are respectively. So over here you have a OH bond. Now this OH bond is going to be very easily, it is going to be converted to iodide. Why? Because there is a good, there is phosphine. Phosphine will be attacked by oxygen, OPPH3, you know that. So oxygen is a very good, oxygen will become a very good leaving group when it is connected to phosphine or silicon at that matter, right? So you are getting phosphine oxide, PPH3 oxygen like this. Okay, so yes, you just got your molecule. The molecule is going to be like this. C and D are completely wrong because you are not getting OH at all. Yes, and you're not getting the hydrolysis over here. It is just the substitution of OH with iodine. Yes, imidazole is working as a base to remove the to remove the proton over the OH. Very simple. Now comes the question that okay, you are carrying out your palladium catalyzed reaction. Very good. You have zinc added, so zinc is going to add up. Zinc is going to add up over here. Zinc iodide is going to form. On the other side, you have this molecule and palladium. So where is the coupling taking place? You have two halogens once again. So the more polarizable bond is going to break first, and that is definitely going to be your bromine. Okay, yes, so you are getting the coupling on the side of bromine, right? So where it is, chlorine and bromine are just the opposite. Yes, so chlorine and the position of bromine just the opposite. So this is how you're getting the coupling. Cyanide stays over here. This is correct. The second one is wrong because one of the chlorine has gone in the presence of bromine. That's not possible. Option number C and D are wrong because the first one is only wrong. The first option is only wrong. So yes, your answer is option number A. I hope that you have seen this question in the previous years and you will see more questions like this. Chalo. So our second question is question number 2. The major product A and B formed in the reaction sequence. So guys, if you want, you can try to stop the video do the question by yourself. Okay, so what do we have over here? We have LDA and allyl bromide. So LDA is very popular for making the enolate like this. And then when you have allylic bromide, okay, there's one more carbon over here. Yes, okay, just one carbon, right? Okay, this is correct. So it is going to attack in this way to eliminate the bromine. So on the alpha carbon you are getting the allylic bromination. ये देखो second reaction, it is your PDCl2. Okay, it is PDCl2O2 CuCl DMF. Once again the same combination that you saw. Wacker oxidation, isn't it? It is Wacker oxidation. And you have this alkene, वो भी mono substituted alkene है, so it will be converted into ketone. Yes, so it is converted into ketone. Now this is your B. This is your B. Who was A? A was your allyl group added on the ketone. Right, this is B. Now guys, in the final step, there is a base and there is a diketone. 1 2 3 4, 1 4 diketone and a base. It is going to give you intramolecular aldol reaction. And yes, the product is also mentioned, the alpha beta unsaturated ketone, not your beta hydroxy ketone, because very easily in the second step, in the presence of an acid H3O plus, there will be dehydration also. So we confirm that you are having the 1 5, or let's say 1 2 3 4, 1 4 diketone. Where is the enolization taking place? From this carbon. Let's say I'm writing a negative charge over here. So this is what you will get. I am directly writing, guys, the 5-member ring on this side. So you will have an OH over here, and then you will have a double bond O on this side, because the middle one is going to be your carbon over here. Okay? Then there is a hydrogen, the alpha proton, more acidic to able to remove this OH group. So your ultimate product is, okay, so sorry, I've just drawn the 6-member ring. Yes, it is going to be like this, right? So that is exactly the same thing. So you're having the intramolecular aldol reaction. Your answer is option number A. Okay, next very good question is, the major product formed in the following reaction is, so guys, what do you see? You see a big molecule and another big molecule, and zinc and palladium and phosphine. So zinc is present. You might think that this is Negishi coupling, isn't it? Let's see. So over here onto this 2-pyridyl anion, basically you are having a negative charge. First of all, this is going to form the organozinc compound like this. First of all, it is going to react with organozinc to give to form like this. Second thing is, palladium will do oxidative addition, where to the position which is also polarizable and to a good leaving group. The methoxy groups are not good leaving groups, okay, not even the amide. Bromide is, or all the halides are good leaving group, and your second position and the fourth position are very, very polarizing, especially the second one. So in this side you have your palladium bromide over here. So now guys, I just hope that you all understand ki how is this reaction going to take place. How is the coupling reaction going to take place? It's very, very simple. First of all, there is going to be, I am writing the step for, transmetallation over here. I've written the transmetallation. There is going to be reductive elimination in this way, and your final product is this. New carbon-carbon bond formation, both of them second position to your pyridine nitrogen. Both of these carbon-carbon bonds are on the second position to the pyridine nitrogen. So this is it. Definitely OME is not leaving. Once again, methoxy not leaving. Once again, amide not leaving. So only answer is option number A. This is your Negishi reaction. Not Megishi, it is Negishi. Okay. Yes, Negishi coupling. Alright guys, we have done few very important questions. एक और बहुत अच्छा question है. Let's do this from CSIR paper only. So major product A and B in the following reaction sequence. Now here you have an alkyne, a terminal alkyne. So you would be very tempted to name it as a Sonogashira reaction. But first let's look at the reagent. There is boron. It is not Sonogashira. It is your simple hydroboration reaction. Hydroboration. Not oxidation, because you're not having H2O2. So first only draw what is necessary. There is a hydrogen, there is a boron, catechol borane over here. Okay, so this hydrogen adds on the less hindered side, and this is a addition like this. One step concerted addition. There is a hydrogen, there is a hydrogen and boron. So guys, doesn't it look like कि alkene जो है, it is a trans alkene? Doesn't it look like a trans alkene? So cis is definitely incorrect. We are having the trans alkene, could be A or B. Okay, now your next step is the coupling reaction once again. So this is your Suzuki coupling. Why? Because you are having a base, you are having boron, you are having palladium, you are having the alkyl bromide, alkenyl bromide to do the coupling. This is exactly Suzuki reaction. And mind this very importantly, that whatever is your stereochemistry at this carbon-carbon double bond, exactly that will be conserved. So your product is going to be in this way. N-butyl, there is a hydrogen, there is a hydrogen trans. Now in the place of boron, you are just going to add the double bond like this. Okay, so one of the alkene is a E alkene, the other alkene is a Z alkene. So E alkene and Z alkene like this. Your answer is option number B. It is wrong in option A, because ultimately it cannot change itself, you know, it has to attach from the same bond connectivity, right? That is the very good thing about your palladium catalyzed reactions. Okay guys, so this was our last question for today, and we have done a lot of reactions in this class, and I hope that you like the video and share the video to maximum people, because this is free. Okay, and yes, I will see you very soon in another good video. Very happy new year 2021 to all of you. Bye and take care.